Hello students, I am Professor Priya Kulkarni from Civil Engineering Department of Parvatibai Genba, Mose College of Engineering, Pagholi, Pune. I am here for the fluid mechanics subject unit 2, that is fluid kinematics and fluid dynamics. Okay, so this second unit is divided into two parts, fluid kinematics and fluid dynamics. Okay, so basically what is whatever we have studied in the first lecture or in the first unit, that is we have studied fluids at the at rest or at steady position. Okay, we have not considered fluid motion. So here we are considering fluids in motion, and whatever the reasons for their motion we'll consider there. Okay, so fluid kinematics is the branch of fluid mechanics that deals with the study of velocity and acceleration. Okay, that means forces and energies is the study of velocity and acceleration of the particles of fluid in motion. Okay, their distribution in space without consideration of any forces or energy involved. So what does basically fluid kinematics says? It is we are considering the fluids in motion, the velocity, acceleration of particles. Okay, and but we are not considering whatever or what are the causes for their motion. Okay, so that is fluid kinematics. Okay, in general we know what is kinematics in physics. Okay, in or in engineering mechanics we have studied the kinematics. Okay, so there we'll consider the subject or fluid in motion, but we don't consider or we doesn't consider the reasons for the motion. Okay, and where we consider the reasons for motion, we'll consider it in the fluid dynamics. Okay, so in dynamics we'll consider fluid in motion, the study of velocity and acceleration of fluid particles, also the reasons for their motion. Okay, so that we'll study in the next part, that is fluid dynamics. Okay, then this the as we know that in kinematics we generally deal with the velocity and acceleration of the particles. Okay, so what does the acceleration field means? Okay, we have taken or we have gone with the examples of any car having some particular acceleration. So what are the uh, points we need to consider? Okay, so that will do the same case with the fluids. Okay, so the acceleration of particle is due to two reasons. One reason is due to fluid particle being convected from one given location to another location in flow, and second location being higher or lower velocity. Okay, that is the first reason. Okay, for the motion. Okay, or acceleration of particle. Okay, so we know if there is a steep slope, then the fluid particle will run very easily, likewise basically, and this is called the convective acceleration. It is also known as adjective acceleration. The second reason is due to unsteadiness of flow, that is due to change in the local velocity of fluid particle as a function of time. This is called local acceleration. So basically acceleration of particle is due to two reasons. One is because of the it is the motion from one location to another, or because of higher or lower velocity, and second reason is due to unsteadiness of fluid, that is change in local velocity of flow with respect to time. Okay, so this is this is local sorry total acceleration is equals to local acceleration plus convective acceleration. Okay, so local acceleration is the due to change in velocity with respect to time, that is dou v by dou t, and convective acceleration is the motion from one position to another. That's why we have considered here u v w, and divided by x y z. X y z are the directions. Okay, in x direction, y direction, or z direction. Okay, so that will give us the total acceleration of the flow. Then acceleration field is the one term that is the we are going to consider here. the portion of material derivative represented by a spatial derivatives is termed as convective term or convective acceleration. Okay, so it represents the fact that the flow property associated with the fluid particle may vary due to motion of particle from one space to another. Okay, then now what we know how to describe the motion of fluid. Okay, so we describe the motion of fluid with respect to velocity and acceleration, with respect to time, direction, likewise. But what are the methods to describe the flow? Okay, so in our syllabus we have two methods for describing the motion of fluid. First method is Lagrangian method and second method is Eulerian method. Okay, now what is the Lagrangian method and Eulerian method? So basically uh, in the first method, Lagrangian method, this method it describes the uh, defined mass, that is position, velocity, acceleration, temperature, pressure, as a function of time. Okay, as a function of time. And in Eulerian method it describes the flow, that is velocity, acceleration, pressure, temperature, as a function of position and time. Okay, so these are the two methods. So in Lagrangian method, the observer concentrates on the movement of single particle. The observer has to move with the particle movement, and the path followed by particle and changes in its velocity, acceleration, density are described. And in this method the observer moves with a motion of fluid. Okay, this is the Lagrangian method. Okay, so basically just remember this thing, it is a function of time, and in Eulerian method it is a function of position and time also. So in this Eulerian method the observer concentrates on the fixed point of the particles. Okay, so these are the two methods of describing the fluid motion. Then the main part or basic part, wherever you go for a fluid mechanics, okay, in your MPSC exam, WRD exam, after completion of your BE, then you will definitely get one simple question on the types of flow. Okay, so just concentrate here. Depending upon the fluid properties, there are so many types of flows, that is real flow, ideal flow, compressible, incompressible flow. And depending upon properties of fluid, that means how the fluid, what is the nature of flow, it is laminar or turbulent flow, steady, unsteady flow, uniform, non-uniform flow, okay, rotational, non-rotational flow, 1, 2, 3 dimensional flow. So we'll see one by one the types of flow, and it is a very important point in the fluid mechanics. Okay, the first one is ideal and real flow. Okay, real flow means it exists. Okay, it implies the friction effects, and ideal flow is hypothetical, it doesn't exist. Okay, so we expect ideal personalities, but they doesn't exist like that. Okay, but ideal real flow exists and it implies the friction. Okay, and ideal flow it doesn't exist, it is hypothetical. Okay, and if we want to uh, explain one theory or one principle, then we assume that the flow is ideal. Okay, by assuming that as the flow is ideal, we can uh, apply the concepts and the thoughts or whatever the derivatives we are going to impose on that particular flow by assuming the flow is ideal. So whenever you see some principles in a fluid mechanics, then there is a first assumption that the flow is ideal, like that. Okay, but ideal flow doesn't exist. And then second one is compressible and incompressible flows. Now, compressible flow is the incompressible flow assumes that the fluid have constant density. So it is incompressible. We cannot compress the flow. Okay, it has a constant density. It is the relation of density for the compressible and incompressible flows. Okay, and while in compressible flow, the density is variable and becomes the function of temperature and pressure. So uh, for example, of for compressible flow, problems involving flight of rockets, aircraft, flow of air in problems concerned with the turbo machines, compressor blades, flow of gases through openings like nozzles. It is example of compressible flow. And what is the example of incompressible flow? So just take a hydraulic problems, flow of gases in machines like fans and blowers. So these are the incompressible flow, where density is constant in incompressible flow and density is variable in compressible flow. So that is the main difference between compressible and incompressible flow. Just remember density. In incompressible flows, density is constant, and in compressible flow, density is not constant. It will vary according to temperature and pressure. Okay, and what is next? It is laminar and turbulent flow, which is very important. So laminar flow, just see this diagram. Okay, the nature of flow. Okay, it is moving parallel. The path, the flow path is becomes very straight. They are not interfering the path of the following flow particles. Okay, and just see the diagram of laminar flow. Okay, the fluid particles are interfering or disturbing the path. Okay, they are traveling in a indefinite way. So that is the flow pattern in laminar and turbulent flow. Okay, also just see these diagrams first, and then how the laminar flow is converting into turbulent flow. Okay, that is the transition of laminar flow from turbulent flow. Now what is the laminar flow? So laminar flow is the sorry laminar flow is the flow in which adjacent layer does not cross each other and move along a well defined path is called as laminar flow. For example, the flow of blood in small veins. Okay, where blood is also having a laminar flow, or flow of oil in bearings, flow of ink in the pen likewise. Okay, so this is the laminar flow. These are the examples. And what is turbulent flow? The flow in the adjacent layers cross each other and do not move along a well defined path. It's called as turbulent flow. For example, flow of river or canal, smoke from chimneys, smoke from cigarette likewise. So they doesn't have any definite path and they cross each other's path. Okay, so that is the turbulent flow. And also the laminar and turbulent flow depends upon one number, that is Reynolds number. In the coming units we will get the idea of laminar and turbulent flow. There is one separate section of laminar and turbulent flow in, I think, fifth or fourth unit. Okay, so it will depend upon the Reynolds number also. Okay, this is laminar flow and turbulent flow. Simple uh, example. Then it is steady and unsteady flow. So for example, steady flow, it is a flow of water with a constant discharge through pipeline. Okay, steady. The uh, and what is unsteady flow? Unsteady flow is a variable discharge through pipe. So when water comes with a uh, uh, variable discharge, or with a very high intensity, and then it will go with a low intensity or pressure, so that type of flow is unsteady flow. And steady means it is having a constant discharge through pipe. So steady flow is the flow in which fluid characteristics like velocity, pressure, density, etc. at a point does not change with the time. So here the this fluid characteristics does not change with the time. Okay, so this is called steady flow. And while in unsteady flow, fluid characteristics means what? density, pressure, velocity changes with the time, that is unsteady flow. Okay, here it is constant and here they are variable likewise. Okay, then uniform and non-uniform flow. So what is the uniform flow? The flow in which velocity at a given time does not change with respect to space. Space means length of a direction of flow is called uniform flow. Okay, so it does not change with respect to space. For example, constant discharge through constant diameter pipe. Okay, that is the example of uniform flow. And what is non-uniform flow? It is the flow in which velocity at a given time changes with respect to space, with, with respect to dimension or direction is called as non-uniform flow. So for example, flow of pipe with a varying cross section is called as or is considered as a non-uniform flow. Okay, then rotational and irrotational flow. So what is a rotational flow? So for example, motion of liquid in a rotating cylinder is a rotational flow. Then for irrotational flow is the flow of liquid in emptying wash basin. Okay, free vortex is called as irrotational flow. So just imagine one basin in our kitchen, and just it is filled with water, and when we remove that inlet or outlet pipe, that strain, then how the whatever the vortex or whatever the rotation of the flow while moving from that pipe, that is called as the irrotational flow. Okay, so the flow in which fluid particles while flowing along a streamline does not rotate about their own axis is called irrotational flow. And in rotational flow, the flow in which fluid particles while flowing along a streamlines rotate about their own axis. Okay, that's the rotational and irrotational flow. You got it? Just see this diagram will clear your concept. Okay, so here the particles are rotating about their own axis, and here the particles are not rotating. Okay, likewise. Then 1, 2 and 3 dimensional flows. Now in the name itself we have cleared that what is the one dimensional flow, two dimensional flow and three dimensional flow. Okay, so although in all fluids are three dimensionally only, but with the pressure, velocity and other flow properties varying in all directions, and in many cases greatest change only occur in two directions, even only in one. So in these cases the changes in other direction can be effectively ignored, making the analysis much more simple. So one dimensional flow is the flow in which velocity is a function of time in one space, okay, or one direction is called as a one dimensional flow. So flow through pipe is considered as one dimensional flow, where uh, we doesn't consider vertical and z direction. Okay, we will consider the flow in horizontal direction or vertical direction only. So that is flow in pipe is one dimensional. Okay, now what is the two dimensional flow? If or if the flow in which velocity is a function of time with a two space coordinates is called as a two dimensional flow. For example, the viscous flow between parallel plates of large extent, or flow of a spillway. Have you seen spillway? It is exactly located, or it is uh, in the dam, and whatever the flow is going or moving from there, it is in x direction and y direction. Okay, horizontal and vertical flow is there. So that flow is called as two dimensional flow. Okay, now what is the three dimensional flow? The flow in which velocity is a function of time and three space coordinate, that is x, y and z also, is called as three dimensional flow. That is, a flow is converging or diverging pipes, or flow in open channels is an example of a three-dimensional flow. The flow in river, flow at the inlet of nozzle are the examples of three-dimensional flow. Okay, so it is a function of all the three directions. Okay, that is the three-dimensional flow. Okay, so these are the types of flow. This is the visualization of flow pattern. Okay, now we have seen what is the types of flow and what are the methods to describe the flow, but there are some important terms that are required for the description of flow. Okay, so that two three terms are there. It is, first is streamline. Okay, what is the streamline? You have heard this word previously also. So it is the curve that is everywhere tangent to the instantaneous local velocity vector. It has direction of a velocity vector at each point of flow across a streamline. So suppose this is the suppose this is the flow pattern, and whatever the tangents we are drawing at the particular point, so that tangent is known as streamline. Tangent to flow is called as streamline. What are the characteristics of streamline, or why it is important to mention the streamline of a flow? So streamlines cannot cross each other, otherwise if they are crossed, they will not be a tangent. Okay, so always it is tangential curve, tangent to the curve. Okay, tangent to the flow curve. Okay, streamline can't be folding line but a smooth curve, and streamline cluster density reflects a magnitude of velocity. Dense streamlines mean large velocity, while sparse streamlines mean small velocity. Okay, so if you have any or if you have seen any flow pattern, so they have mentioned, they doesn't mention that the type of flow or whatever the velocity and type of flow. So they just draw the they just have the graph of the streamlines. Okay, so accordingly they'll get concluded that whatever the density and whatever the type or whatever the velocity of flow at that particular point. Okay, so that's why streamlines are very important. And one more point is, or one more line is path line. Okay, path line is the actual path traveled by an individual fluid over a particular time period of time. Okay, same as fluid particles, and the path of particle same as streamline or steady flow. Okay, now just for example, see, this is the fluid path. Okay, so what is the tangent is known as streamline, and what is the actual path the flow is traveling is known as path line. So this is path line. Okay, and streak line and stream tubes. Streak line is the locus of fluid particle that have passed sequentially through a prescribed point in a flow. So it is easy to generate in experience like dying in a water flow, smoke in an air flow likewise. So these are the fundamental terms that we are used for mentioning or for explaining what is the type of flow and what is according to it we conclude what is the density velocity of that particular flow. Okay, so stream tube is imaginary tube whose boundary consists of streamlines. Okay, so so these are the streamlines, and it is imaginary tube. The volume flow rate must be same for all the cross sections of a stream flow. Okay, then circulation and vorticity, it is an important term. What is the circulation? Circulation, in name itself it is explained. So circulation and vorticity are two primary measures of rotation in a fluid. Circulation, which is a scalar integral quantity, is a measure of rotation for a finite area of fluid, and vorticity is a vector field that gives microscopic measure of a rotation at any point in the field. Okay, this is for scalar and this is for vector function, and it gives the characteristics of flow in short. Okay, it is a moving in circular direction, and vorticity means it is not in exactly circular but in any other direction or in any other way. Okay, so same circulation and vorticity. So stream function, okay, uh, it is defined as a scalar function of space and time such that the partial derivatives with respect to any direction gives the velocity component at right angles to that direction. It is denoted by psi. Okay, psi, and it is for two dimensional flow. Okay, so it gives a function, it is a scalar function of a space and time. Okay, and velocity potential function, it is a scalar function of a space and time such that the negative derivative with respect to any direction gives the fluid velocity in that direction, and it is denoted by phi. Okay, well, stream function is denoted sorry stream function is denoted by psi. Okay, this symbol is psi, and velocity function is represented by phi. Okay, and negative sign, it is actually a negative derivative with respect to any direction. Okay, the negative sign indicates that flow takes place in the direction in which phi decreases. Okay, so just remember these two functions very carefully. We have some simple numericals on these two. Okay, so this is the relationship between stream function and velocity functions. Okay, just remember this carefully. So what is difference between stream function and velocity potential? Stream function is for only two dimensional flow, velocity potential is for all dimensions. Okay, so that's why we have considered here u, v, w. Okay, for x, y and z direction. Okay, and it exists for viscous and non-viscous flow or stream function, and velocity potential, it is irrotational. Okay, for zero velocity flows, zero viscosity flows, and it is for incompressible, steady or unsteady, but velocity potential is for incompressible flow, steady and unsteady flow. Okay, so this is the basic difference between stream function and potential function. So by using these streamlines and path lines, we can draw flow net. So what is the flow net? It is a grid obtained by drawing a series of streamlines and equipotential lines. It's called flow net. So these are the streamlines and these are the potential lines. So by joining these two type of lines, we'll get the flow net. Okay, so flow net provides a simple graphical technique for studying two-dimensional irrotational flows when the mathematical calculation is difficult. Okay, and the streamlines and equipotential lines are mutually perpendicular to each other. Just remember this very carefully. The streamlines and equipotential lines does not cross each other's path. Okay, they are always perpendicular to each other, and a flow net analysis can assist in the boundary shapes. What is the boundary shape? This part is there in your syllabus. In the 5th or 6th unit, we'll get the idea about the boundary shapes or boundary functions. Okay, and it is used for calculation of flow velocity. Okay, so by using this flow net, we can uh, mark our analysis for the complex flows where we cannot do in a mathematical way. Okay, so that is the flow net. Now whatever the next part is there, we'll see in the second session. So for this is the basic idea for explaining or for mentioning, describing the nature of flow. Okay. In the second session, we'll see what is the actual mathematical ways to calculate the velocity and discharge of the flow. Okay. Thank you.